The stillness beneath the waves can be deceiving. Imagine a colossal 18,000-ton attack submarine submerged in the ocean, effortlessly cruising past the profound silence of the deep. Each contoured hull section is engineered to withstand immense underwater pressure, a titan of steel silently stalking through its aquatic domain. However, as it descends deeper, the water enveloping it exerts a crushing force, one that can reach over 4,000 pounds per square inch. In this underwater world, the very machinery designed for exploration and power must withstand more than just the weight of the ocean, it must confront the physics of pressure itself. But here lies the paradox: how does a machine like this, designed to operate near its crushed depth, somehow stabilize its own structure while plunging into an environment where most materials would succumb? In the next few moments, we will unravel the complexities that allow these extraordinary vessels not only to dive deep but to thrive in conditions that would destroy lesser machines. The answer lies in a remarkable engineering principle known as prestressing. A submarine's pressure hull is specifically crafted to endure the profound pressures exerted at significant depths, pressures that many would assume would lead to immediate collapse. Yet, the reality is quite the opposite. While one might envision the hull buckling under the relentless weight of the ocean, engineers have realized that by intentionally prestressing the steel, they can create a powerful, self-stabilizing mechanism. To fully understand this, we must first examine the physics of pressure. Water is dense, about 800 times denser than air. At a depth of 1,000 feet, even a massive submarine encounters nearly 450 pounds per square inch of water pressure. To illustrate the significant forces at work, consider that when a submarine dives, every square inch of its hull feels the intense weight of the water compressing it inward. Yet, instead of crumpling like a soda can, the hull itself is designed to deform elastically, meaning it can bend and flex without permanently losing its structural integrity. One significant example of this phenomenon can be observed in the Los Angeles-class submarines, which feature a pressure hull constructed from high-strength steel that is an astounding 6 inches thick in some areas. The elastic properties of this material allow it to accommodate significant deformation at depths that would challenge the very structure of ordinary materials. While many assume that increasing the thickness of the hull would be the solution, engineers actually find that excessive thickness introduces newfound challenges with weight and maneuverability. This brings us to the next layer of complexity. Why pre-stress the hull? The reason becomes evident when we delve into the idea of stability. As the pressure envelopes the submarine, the pre-stressed material counteracts the ocean's force. Imagine dragging a heel downhill. If you brace yourself and lean into the slope, you become steadier. Similarly, the submarine's pre-stressed hull actively pushes back against the crushing force, creating a balance that maintains its shape even as external pressures rise. Without this careful engineering, the hull would collapse inward, succumbing to the relentless weight of the water. Yet, there is an apparent contradiction in how we tend to visualize force. It seems intuitive that if something is subject to compression, introducing more material should handle the load better. This leads many to believe that a thicker hull plate is the solution. However, this notion dismisses the critical balance between weight and operability. Thicker steel may offer some initial security but at the cost of increased inertia that affects quick maneuvers. The goal is to have a resilient structure that can withstand dynamic stresses while maintaining the ability to move seamlessly underwater. Another excellent example is found within the newer Virginia-class submarines. These vessels utilize advanced composite materials alongside their hull designs, allowing them to decrease overall weight while retaining toughness. They incorporate composite materials such as carbon fiber and titanium, which give them the necessary durability without sacrificing buoyancy. This engineering evolution demonstrates a significant leap forward, showcasing how innovative materials can withstand the same pressures with a lighter footprint. Now, you might be wondering, how do engineers determine the crush depth for these submarines? The concept revolves around the term maximum operating depth, often referred to as the crush depth. For the Virginia-class submarines, engineers estimate that this threshold is roughly 800 feet or approximately 244 meters. But what happens as the submarine approaches those limits? At depths approaching the crush limit, the hull begins to exhibit controlled elastic deformation. To visualize this, consider a rubber band being stretched. As you pull it, it expands but still retains its original shape. This gradual deformation is monitored with advanced sensors and gauges that provide real-time pressure readings. These readings allow for precise adjustments in buoyancy and trim, ensuring constant stability. Engineers cleverly designed submarines to remain just below this critical threshold. They achieve this real-time flexibility by incorporating a system of ballast tanks that can adjust the submarine's weight and buoyancy quickly. By pumping additional water in or expelling it, submarines can engage in nuanced maneuvers, keeping themselves firmly positioned just above the point of catastrophic failure. This precision in engineering ensures that submarines operate with an unyielding rigor while threading the needle of extreme ocean depths. Midway through our exploration, let's pause for a moment. Imagine standing next to a colossal construction machine or even a nuclear power reactor, massive in scale and engineered for complexity. Which of these machines would you least want to be standing next to? Consider the layers of engineering that hold them together, the invisible forces at play that dictate their integrity. Now, let's pivot to the intriguing misconception regarding hull construction. Many of us might believe that submarines should be designed to completely resist the pressure of the ocean by thickening the materials and becoming ultimately impenetrable. This idea oversimplifies the challenge of underwater engineering. In reality, engineers accept and embrace the controlled deformation as a mechanism for strength. By allowing the hull to flex within predetermined limits, they enhance the vessel's resilience to catastrophic failure. The misconception is that rigidity is synonymous with safety. The truth lies in the delicate orchestration of controlled flexibility. To encapsulate the brilliant engineering behind submarine design, we can ask ourselves a simple question: how do submarines survive the depths of the sea? The answer is profound in its simplicity: they crush themselves to dive deep. By designing the hull to engage in controlled elastic deformation via pre-stressing, naval architects allow the pressure exerted by the ocean to strengthen the structure rather than weaken it. In closing, consider the grandeur of these marvels as they navigate through mysterious depths. The ingenuity behind their design and the invisible mechanics that allow them to function tap into the immense creativity of engineering as a discipline. Each submarine is a culmination of knowledge, precision, and an understanding of physics that transcends initial perceptions. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you. To further illuminate our understanding of how nuclear submarines manage the immense pressures of the deep, we should consider the role of hydrodynamics and how submarines move through water. This aspect of their design directly influences their ability to navigate extreme depths. The term hydrodynamics refers to the behavior of fluids in motion, and in the case of submarines, it is vital not just for propulsion but also for structural health. As a submarine travels through the water, it creates a flow pattern around it. Think of a stone dropped into still water, it generates ripples that extend outward. The design of a submarine must account for these flows to minimize drag. A streamlined shape reduces the impact of water pressure on the hull, allowing for smoother navigation and less energy expenditure. For example, the Virginia-class submarine is designed with a teardrop shape which allows it to efficiently slice through water, encountering reduced resistance while increasing speed and maneuverability. Another important element in submarine pressure management is the ballast system, which plays a crucial role in diving and surfacing. Ballast tanks are chambers within the submarine that can be filled with water or air, allowing the vessel to adjust its buoyancy at any given moment. By filling these tanks with water, the submarine increases its density and descends. To ascend, it expels the water and allows air to fill the tanks, decreasing its density. This dynamic ability not only aids in descent but also assists in controlling the rate of pressure experienced by the hull. Engineers design the ballast system to operate in unison with the pre-stressed hull. When the submarine dives, it allows the external pressure to be met with pre-stressed structural integrity, ensuring a smoother experience as pressure accumulates. To illustrate the efficiency of this mechanism, consider that Virginia-class submarines have a submerged speed of about 25 knots, with a range that allows them to travel vast distances without surfacing. While examining the operational depth of nuclear submarines, it is also essential to highlight the ever-present threat posed by underwater terrain and geology. A submarine must navigate not only the pressure of the water but also the potential hazards lying beneath the surface. Underwater mountain ranges, jagged cliffs, and shifting geological formations can produce unpredictable currents and turbulence that further complicate deep-sea navigation. Submersibles facing such dangers utilize advanced sonar systems that map and interpret the ocean floor. The sonar bounces sound waves off underwater objects, allowing the submarine to create a real-time picture of its environment. This technology plays an essential role, ensuring that submarines navigate the depths with synchronous intelligence. It is akin to driving in total darkness with only the sound of echoes to guide you. It requires an intricate understanding of surroundings to avoid catastrophe. Now, let us take a moment to dive deeper into the history of submarine engineering. The early days of submarines were fraught with challenges in pressure management. For instance, consider the designs of the early 21st century submarines like the Charlie II class used by the Soviet Union. They suffered from hull integrity issues because their materials were not sufficiently pre-stressed or robust. Submariners often referred to their operational depth as uncharted territory due to a lack of data on pressure elasticity. Tragically, submarines like the K-219 suffered fatal accidents, dramatically illustrating the potential consequences of neglecting the physics of pressure. The evolution in design, materials, and operational philosophy since those early submarines has changed dramatically. Modern nuclear submarines testify to the integration of advanced materials science, physics, and engineering practices that promote not just survival but enhanced capabilities in extreme environments. This expertise often leads to R&D focused on next-generation materials. For example, the incorporation of hydrogen-solidified steel is being explored, which increases durability while significantly decreasing weight. The lift-off potential of these advanced materials allows submarines to operate more efficiently while maintaining the needed resilience against crushing underwater pressures. As we consider the sheer scale of these vessels, the materials and their properties stand at the forefront of submarine engineering. Steel's tensile strength under compression becomes crucial when discussing the inherent risks of diving to extreme depths. Common ocean pressures exceed 10 tons per square foot at 2,000 feet, and safety factors must be implemented to ensure consistent performance. Engineers perform extensive computer simulations based on real-world data to understand the relationship between size, shape, and structural integrity, crafting designs that balance performance and safety. Keep in mind the sophisticated tracking and emergency systems within each submarine. Dive may sound like a simple order, but behind it lies a labyrinth of monitoring systems designed to continually assess the submarine's integrity and depth. Control surfaces help to monitor and adjust the orientation of the submarine, which is crucial during both ascent and descent. Consider an emergency scenario. If a submarine were to experience a malfunction during descent, structural integrity sensors would initiate an emergency ascent protocol, relying on real-time buoyancy controls along with precise ballast management. This requires engineers to create redundancy systems. A simple backup pump can mean the difference between a safe return to the surface and disaster in the depths of the ocean. Reflecting on the narrative of submarines and the critical balance between pressure and structure, we see that engineering is a blend of art and science. The coastal waters might seem calm on the surface, but below lies a world of extreme conditions requiring advanced technology and ingenuity. At the end of this examination, we can reflect on an intriguing principle in submarine design. Just because they need to resist air doesn't mean they should ignore the beneficial aspects of allowable deformation. The careful modulation of pressure against perceived rigidity opens up a realm of understanding as we explore the capacities and capabilities of nuclear submarines. Imagine, then, how generations of engineers, mathematicians, and naval architects have grappled with these principles to protect the lives of those who serve aboard. With the understanding that a flexible design can lead to a more robust submarine, we appreciate the depth of foresight and complex planning that fuels each remarkable dive into the abyss. All around us, in the engineering feats we entrust our safety to, the principles of physics and materials science work in conjunction, often invisibly, to uphold the realities of strength and resilience. As we close our exploration of the machinations behind nuclear submarines and their engineering marvels, it is essential to remember the delicate balance of design elements that ensure their survival in the harshest realities of the deep sea. The bigger the machine,